Okay, so welcome to Math2526. So today we will continue this topic, type 1, type 2 error. Okay, so in making our decision, like in set down the two arguments, H or HA, we may make some mistake, right? So we say we may make those two kinds of mistake. Refuse HO when HO is true, or accept HO when H was not true, right? So those two mistakes, we say we refuse HO when H was true, the type 1 error, and so we accept HO when H was not true. This is type 2 error. So usually we say type 2 error is more serious. So okay, so like we usually will not believe people, right? We should refuse people. What our first reaction usually is refuse. Then only after we collect some information, then we can accept the claim, right? Okay. So once we have a decision-making law, we want to check whether the law is good or not so good. So how can we check? How can we say the decision-making law is good? Or we can apply decision-making law is good. Then we can apply. Then we need to check alpha and beta. So we discussed those kind of problems before, right? Let's say, suppose for this hypothesis, HO is mu equal 3.00, and we believe. So here we talking about a GPA, right? Average GPA. So we say maybe not so good. GPA will be less than 3.00. So our decision-making rule is like this: if x bar is this, okay, so here's 3.00. So if x bar is less than this, cut point 2.95, we will reject. So if they have a small distance, like 0.005 distance between the two numbers, we believe such a distance is big. Okay, so decision making law is like this, right? So here we say this part we will reject, and this part we will accept. Okay. So for this decision-making law, we want to find alpha. So such a problem we discussed in last class, but as a review, let's do this again. Let's check that problem. So alpha is type 1 error, or refuse HO when H was true. So refuse HO, we say when this part x bar less than 2.95, we will refuse. So when H was true, when mu is thus. So when mu is equal 3.00, so we can find that when H was true, we can have the distribution for x bar. So x bar again follows us, like mu and sigma over radical n. Okay, so here what is sigma? Yeah, so sigma, it says sigma equal 0.3. They claim mean is at least this with standard deviation 0.3. So there's a 0.3 is a sigma, is population's standard deviation. Okay, so when x bar follow this normal, find the alpha. So such a problem is just find a population for normal distribution, right? So such a problem we have a standard process. So changing this to general standard normal, from general to standard normal. Then so from here then check check the table. Okay, so let's check 0.67. 0.67. Okay, so suppose like we just check the table. No more table. Do we have? Okay, so 6, 7, 6, 7. So this is 7486, 7486, but that means 1 minus here. So this equal, let's say 4152. Okay, so this is 2514. So let's go back. Okay, so this equal 2514. So such a probability we say, oh, quite large, right? 20% chance for make a mistake. So this is quite large. So we can say, oh, such this law is not good. Like we have a really small difference, you just reject. So such a decision is not so good, right? So this makes sense, right? We can say like 0.005, the same as 0.005 is small difference. So you should not reject. If we reject, then you have so much chance to make a mistake. 25% chance to make a mistake. Okay, so we say such a decision making law is not so good, right? So we have another. So we have this question: how can we set a good decision making law? Right? How to set a good decision making law? So good means we want to guarantee to apply your decision making law, the alpha will be not so big. Okay, so let's look at the same problem. Now, some people claim average GPA in this for all students is 3.00 or at least 3.00 with a standard deviation 0.3. So to test, okay, to test their claim, we intended to do a survey. So we set this decision-making law first. Then we can apply this decision-making law to make our decision, right? Okay, so suppose that we will check the decision-making law, check 16 people, and if X bar less than this cut point L, we will reject. Okay, so decision making law is so suppose here is 3.00. So we said L is here. So if X bar is less than this number, we say we will reject. So otherwise, we will accept it. Okay. So we want to find this L, such that we want to guarantee alpha is 0.05. Like apply this decision making law. Make type 1 error is only at the most 0.05. So what is this L is? So we say like from previous example, if L equal 2.95, this is not so good, right? Because alpha is like about 25%. So this is like this number is too big, like too close to 3.00. So here we need to find such a cut point L that make it alpha 0.005. Okay, so let's check. So alpha, by now we know alpha equals 0.005. So 0.005 is this probability for this type of mistake. Diffuse HO, when HO true, so diffuse HO is here. X bar less than L, we will diffuse. So when HO is true, meaning mu equal. So again, like when XO is true, or when mu equals 3.00, we know the distribution for X bar is like this. X bar follows this normal. Mean is 3.00, standard deviation 0.075. Okay. Okay. So the question now is find L, find a cut point. We know the probability 0.005. We want to find a cut point. So for such a problem, at first we change to standard normal, change to Z. So Z less than this number, and if less than this number, then probability 0.005. So we need to find this number. Okay, so now let's see. So let's check a standard normal. Okay. So here we want to find this cut point such that this is 0.005. Okay. So we find this number first. So from this standard normal, we want to find this cut point. Okay. So the first reason, we know this is negative number, right? So we just check this cut point, this number. So this part 0.005, and so we know so left side for this cut point is 9500, right? So we need to check point 9500. So we want to find this cut point, right? Okay, so from the normal table, find this cut point 9500. So let's check normal table. Okay, here it is. So this is no stand normal yet. So we need to check 9500. 9500. So we find a neighborhood for 9500 here. Okay, so 955 is between them. So we just pick the closer one. But if we find the distance for them to 0.9500 the same. So in this case, we can pick either one, right? So we can, if we pick this one, we put 1.64, pick this one, 1.65. Okay, so we know if this is 9500, then this cut point should be 1.64 or 1.65. Okay. Okay. So then this cut point like a 5%. So here 0.005 is negative 1.65, right? Okay. So now let's go back to our problem. Okay, so here we consider this number as negative 1.64, or negative 1.65. Okay, so then we can find this L. So L equal 3.00 minus 1.64 multiplies thus, right? So the cutoff point should be this number. Okay, so let's see. So here a little bit of calculation. 1.64. Okay, so we can put it like this. This equal 2.88. Okay, so the cutoff point should be this 2.88. So, so 2.95 is too close, right? So this L equal, we should set this cutoff point L equal 2.88. So if x bar is less than 2.88, then we should reject. So use this decision making rule, we can guarantee alpha is at the most is 5%. Okay. Okay, so this problem is just that we want to, so once we have a decision making rule, we can find alpha. So here, in order to guarantee we have this alpha, we want to set our decision making rule, right? Okay. Okay. So now, once we have a decision making rule, we can find alpha and beta, right? Sometimes. So let's check this problem. So some people claim the average SAT, right, for all students is at least 580 with standard deviations 100. So this is other people's claim, average 580, standard deviation 100. So we don't believe, maybe we don't believe their claim. We will believe, we will adopt maybe the average exam score will be less than 580. Maybe not so high, right? So we said HO is equal, HA is less than. So how can we make our decision HO, HA? So we set this decision making rule. So if here 580. So we just put this cut point 576. So like if they have 4 points difference, we can believe this difference big. Okay, so if x bar is here, then we say difference big, we will reject HO. Right? If x bar is difference is not so big, like a 578 or 2 point difference, or 579 or 1 point difference, we will accept the claim. Right? We will believe average will be 580. Okay. Okay. So once we set this decision making rule, so we can find alpha. We can find alpha. So this problem we just discussed it before, so we leave this for you as a practice. So let's check beta. Okay. Okay. So suppose we want to find a beta. So what is beta? Beta is type 2 error. So type 2 error, by now we remember, just accept the claim. At the first step, we just accept it, but their claim is wrong. Just accept long claim. So we accept HO when HO is not true. Okay, so accept HO. So when we will accept, so we say this part will reject, but this part will accept, right? So accept HO when x bar larger than 576, we will accept, we will believe their claim, right? So we accept this when HO is not true. So HO say mu equal 580. But when HO is not true, is mu not equal. If HO is not true, then we should pick HA. So we believe mu will be less than 580, right? Okay, yeah. So when HO is not true, we just pick HA. So mu will be less than 580. Okay, so we want to find the probability. So we say that if we want to find out there's a probability x bar larger than 567, we need to know the distribution for x bar. So x bar follows this. Yeah. So x bar follows this. No more mu sigma of radical A. So here we have some trouble. Like we don't know the exact value for mu. We only know this mu will be less than 580. Right? So we only know mu less than 580. So even though we know there's sigma, or we know there's n, let's say sigma is 100. So this one, yes, sigma is 100. N is we know, like take sample size 25. Okay. Fine. Okay. So for mu, the information about the mu is we only know mu less than this mu less than 580, right? Since we don't know exact value for this mu, then we cannot calculate this beta. We cannot find this probability x bar larger than 576. So even though x bar follows this normal, but we don't know mu. Okay, so we cannot find alpha. No, I'm sorry, cannot find beta. So the problem is like when HA is true, we still don't know exact value for mu. Okay, so this is the reason we cannot find beta. So in order to for beta, only for some typical situation we can find the value for beta. So this typical situation we call the 2-point hypothesis. So this is the simplest hypothesis. Okay, so like this, like with 2-point HO is, we say mu equals this number. HA say mu equals this number. Okay, so for mu we have only 2 possible values. So we needed to determine which one So we say we set the decision making rule. So we say if okay, we just take a sample, right? So sample size 25. So what decision making rule is like this. Cut point is 12. We just set as 12. Cut point. So if x bar is less than 12, then we say this part is HO. If x bar larger than 12, this part is HA. So our decision making rule is really clear, right? So if your x bar is less than 12, HO, larger than 12, HA. So we can set down the arguments. Okay. So for this decision making rule, so let's check. We can find alpha, find beta. Okay, so let's check alpha. So alpha is top 1 error. So top 1 is refuse HO when HO is true. Okay, so let's say when we will refuse HO, so when x bar larger than 12, right? Yeah, so here we say HO, we accept HO. Here we will reject HO or support HA. So refuse HO means x bar larger than 12. So when HO is true, when the mu equal 10. So if we know mu, then we can find the distribution for x bar. So x bar, x bar just follow this normal. X bar follow this normal. Mu, so sigma over radical A, right? So mu equal, let's say mu equal 10. So mu equal 10. Then sigma, let's say sigma equal sigma, say assume that sigma is 5.5. Okay, so sigma is 5.5. 5.5. So divided by radical 25. So we choose 5. So we find this x bar follows this, right? 10, 1.1. Okay, 10.1.1. So we know that the distribution of x bars, then we can find the probability about x bars, so we can find this probability. X bar larger than 12. So this is alpha, right? So find the probability. So we say the binomial become routine. So this minus mu divided by sigma, right? So that's equal C larger than, so larger than, so that's equal to divided by 1. Okay, so 1.82, 1.82. So now we just check the table. We can find this probability. Okay, check the table. Okay, 1.82. So 1.82. So this is 9656. So 1 minus, so that's equal 4450. So 00544. So we say alpha, so okay, equal so how about the beta? So beta is type 2 error. Type 2 error is we accept accept their claim when their claim is wrong. So here we just accept HO, accept HO when HO is not true. Okay, so accept HO when HO is not true. So accept HO. So let's check out when we will accept HO. We say like here we will accept HO, right? Less than 12, we will accept HO. Okay, so here accept HO means x bar less than 12. Accept HO, right? So when HO is not true, so HO say mu equal 10. But so not true. So here HO say mu equal 10. So not true, we can only pick this because we assume possible value for this P has only two possible values. If not equal this, then has to equal that. So we just pick mu equal 15, right? So mu equal 15. Okay. Okay. So when mu equal 15, so we know the distribution for x bar follows this. So like follow this, so formula the same. X bar follow this normal mu sigma over radical n, right? So here same thing. Mu, so mu equal 15. And the sigma 5.5, n is 25. So 5.5 over 5 is 1.1. So we know x bar follows this normal. So the question becomes like when x bar follows this normal, we need to find this probability. X bar less than 12. So such a problem is just like a routine, right? So let's finish this. So x bar less than 12. Okay, so then there's changing to z less than, so here this minus mu, so by now mu is 15 over sigma is 1.1, so this equal, let's see, so z less than, okay, so this equals this divided by 1. Okay, 2.73. Yeah, so that's equal negative 2.73. So from the Z table, we can find this. So let's check 2.73. 2.73. 2.7. 2.73. This one, right? So 9968. So 9968. So 1 minus, yeah. So this equals 0, 0, 0, 3, 2. So this 0, 0, 3, 2 is beta. Okay. So let's see. So finally we find this equal 0, 0, 3, 2. Okay. So in such a situation, we can find alpha and beta, right? So we say for this 2-point distribution, we can find beta. So find beta because when this is true, we know mu. So find alpha, so we say usually we can find alpha because alpha is HO or is equal. So when HO is true, we know the distribution, we know the mu, right? Okay. So from this example, we say, oh, here alpha is small and beta is also small. So this decision making rule is good. Okay, so we say this alpha and beta. Alpha and beta are the probability for making mistake. So we prefer those numbers are quite small. Right? The smaller the better. So the question is, can we set them as 0? Alpha equals 0, beta equals 0. So this means, according to your decision making rule, apply your decision making rule, we will never make a mistake. So it sounds good, but actually, but actually such decision making law is useless. Just like for confidence interval, right? If we want to make if the confidence level is 100%, if we wanted to make a decision without any mistake, then our decision, our conclusion is useless. Right? For example, if we wanted to predict or wanted to estimate people's lifetime or longevity, we say, oh, people's longevity between 0 to 200 years. So this is completely true, but such a conclusion is completely useless, right? So here again, like we cannot set alpha or beta, both of them to be very, very small, because like this become like too conservative to make any decision. We cannot make any decision because like when we make a decision, we always have some risk that our decision maybe is wrong, right? Okay, so so today is we just finished the topic type 1 and type 2A, and then we just finish our part 2. For statistical part 2, so we call one sample problem. So from one sample, we can do estimation and do hypothesis testing. So for testing, we also want to check whether how much chance that our decision is wrong, right? So we check type 1 error, type 2 error. So type 1, type 2 error is a very common mistake when we when like for other people's claim or other people's suggestion or reaction, we will believe them, we will listen to them, or we will not believe them, not listen to them. So our reaction will have these two kinds of mistake, right? Just like we do not believe them when their suggestion is good. So this is type 1 error, right? And we will believe them, we will accept their suggestion, but their suggestion actually is wrong. So this is type 2 error. Okay? So you got the idea of type 1, type 2 error. Okay, so we can stop here.